Good morning, everybody. We're going to start the presentation of this conference entitled Computer Vision. And the first work is presented by Juan Carlos Belén Luna, entitled Pattern Recognition of Popularity Reflex Dynamics to Isoluminescent RGB Chromatic Stimuli. So please use your time, to all the presenters, use the time for no lost more time because you know that we have some minutes late. So,
Thank you. Hello, good morning, everybody. My name is Juan Carlos. I'm from Simvestab of Mexico City, and our research topic is pattern recognition of popular reflex dynamics to isoluminescent red, green, and blue chromatic stimuli. An overview of the presentation. First, we have the introductions. Next, the objectives, the hypothesis, instrumentation, the experimental instrumentation, subjects characteristics, the stimulus characteristics, and the methodology, and finally, the results, conclusions, and future work. Introduction, when light enters the eye through the cornea and the diameter of the iris, light beam is controlled by means of the iris muscles that form the diaphragm of the eye. The opening formed in the iris is called the pupil. The pupil's light reflex considers like a servomechanism because the pupil functions as a regulator of light that impacts on the retina, and it is part of the sympathetic and parasympathetic system. For the study of the pupil size, it is essential exposed to a stimulus in a punctual way. The pupil is a good regulator of light since the response to light are influenced by its initial size. After a contraction due to illumination, a slow dilatation occurs and the pupil returns to its initial size. In the medical field, the pupil area can be used to support a doctor's decision for early detection of diabetes with the pupil light reflex method detecting abnormalities in the pupil area in diabetic patients. What is our objective? Is identify, classify, and compare pupillar reflex based on directions to chromatic light stimuli under the same conditions and the specific objects. First, we developed a high precision non-invasive optical instrumentation for quantitative analysis of pupillar response under control conditions, capture the image of pupillar reflex to visual evoked potentials with chromatic luminous stimuli at the same luminance, and next generate the database, image processing with computer vision techniques, and finally analyze pupillar reflex response to colors. The hypothesis and objective correlation between the pupillar response and the visual evoked potential in response to chromatic stimuli presented under the same luminance is expected. The experimental instrumentation system was designed to find pupillar reflex using the consensus light reflex. First, we record the subject's right pupil for 4 seconds, where the stimulus is projected for 10 milliseconds on the left eye. This process is repeated 3 times for each red, green, and blue color, and the distance once to the stimulus, to the eye, is 30 centimeters. The distance to the aids to the lens of camera is 8 centimeters, and the distance 3 is the same. In this slide, we have all the instrumentation. First, we have the Goldman perimeter. The Goldman perimeter, and 2 is the stimulus with a LED. 3 is the control system with electrical components and Arduino. And this 4 is the DC source. 5 is all the ophthalmological support. Is this? An adjustable bench for the subject to adjust up the level of the subject for the recording. And 8 is the infrared ring. 9 is the PC with the software for the camera. And 10 is the camera. 11 the background illumination with LED strips. And 12 is a Faraday cage to suppress the noise in the environment. In this slide, we have a sum of the Goldman perimeter. First is the Goldman perimeter. 2 is the stimulus, in this case with a LED. 3 is the chin support. The chin support is to level the subject to the recording. 4 is the movable base. The movable base have movement in the X and Y axis. And 5 is the DC source to the LED strips. 6 is the ophthalmological support of the ophthalmological support. 7 is the infrared ring. And 8 the camera. 9 the forehead support. And 10 is the background illumination. What about the subject's characteristics? In this case, the participants should preferably not have refractive problems, and the participant will be asked if he or she suffers from myopia, hyperopia, presbyopia, or astigmatism to take in account during his or her participation. The established age is from 18 years old to 99 years old. The Ishihara test will be applied to all participants to determine if they suffer from color blindness, and the participant will be asked to answer a questionnaire where he or she will be asked about his or her conditions. Before participating in the test, if they do not pass, their participation will be suspended and we will continue with the pertinent. And what about the stimulus characteristics? The stimulus luminous projected to the participants has a luminance of 93.19 candles per square meter, and a wavelength or lambda to the color red, the 6300 to 6350 nanometers, the color green, 490 to 540 nanometers, and for the color blue, 550 to 500 in nanometers. And the background luminance inside the comal perimeter with the LED strips is 1.03 candles per square meter to adapt the pupil to an intermediate level, not fully contracted and not fully dilated. The stimulus inside is a 1 watt ultra bright light diode of the red, green, and white, red, green, blue, and white type, and the stimulus is located at a separation distance of 30 centimeters. 3 shots are considered for each color with a duration of 10 milliseconds, and a pause between each of the shot of 10 seconds. The methodology: first, we recording pupil activity. Next, with the recording, have a extraction and selection of pupil frames, and a processing and calculation of pupil areas with all the pupil frames, and to generate a storage database. This database is an Excel file, and finally, data analysis. We have 2 algorithms. In this case, the first algorithm begin with the video recording, and we create an algorithm with Python and OpenCV. We extract all the pupil frames and have a frame selection. The frame selection, we have finally a total pupil frames, and the second algorithm, we have all the total pupil frames, and with other algorithm and Python and with OpenCV, we calculate all the pupil areas, and the pupil areas generate a file in Excel with all the areas and create a database, and we graphing. The process of the image, in the first stage, we have the preprocessing. The preprocessing begins with the resizing with the original image. Next, we have a grayscale of the image and smoothing and equalize it. And in the second stage, we have the segmentation. The segmentation begins with a threshold of the equalized image, and next an operational morphological with closing, and finally the border detection with the Kenny. In the 3 stage, we have the post-processing, and in the Kenny, we apply the ellipse adjustment to finally obtain the pupil area. And in the figure 8, we can see the calibration with a 1 millimeter checkboard image. The results at the moment. At the moment, we have the recording of a subject with the subject 6. In the graph, we can see that the pupil area is different for each color. We have the shot, and we have the contraction of the pupil. Next, the redilatation, and begin the no. First, we have the color red, next the color green, and finally the color blue. And in each of these experimental is different the results for each activity of the pupil. Other experiment with the subject, pupillar reflex of the subject during 10 repetition to the color, and in this case red, green, and blue, that the results of the color red, the color green, and the color blue. In this case, each graphic is a different with in the index 1 to the number 10. We can see that the pupillar activity is the same in this case with this subject, because we have an area of contraction on each of the shots, the same. Conclusions. At the moment, development of this innovative BOG system has made it possible to accurately capture pupillar activity in a controlled environment, and based on the results, so far we assume that the subject's pupillar reflex is similar, and with the use of machine learning techniques, we will validate or refute this inference. It is important to note that the repeatability of the test can be effectively scaled to a significant level of individuals, thanks to the rigorous control of all variables elements involving during the recordings. And the exhaustive processing of analysis of pupil frames allows the classification of patterns in pupillar activity by comparing them with the results obtained from pupillar reflex to a color stimuli for each subject. What is our future work? The next step in this research will involve the recording of subjects with different genders and age, and involving the analysis of colorblind, in this case intoxicated, and diabetic subjects to build an extensive database. And this approach will allow the classification of patterns in pupillar activity, which will be fundamental for the identification to significant trends in relation to response to the color stimuli. Identify parameters of the pupillar response, such as contraction and redilatation velocity, the contraction and redilatation times, the pupillary latency, initial pupil area, and minimal pupil area. And finally, apply machine learning techniques to the data obtained for classification and clustering for the development of a biometric identification system based on pupillary response. And that's all for me. Thank you very much.
Thank you, Juan Carlos. Now it's time for questions. Okay.
Gracias. So, first of all, congrats. It's really interesting work. My question is, I'm curious about why are you using thresholding instead of other segmentation algorithms?
En este caso, voy a responder en español. En este caso, nosotros en el tratamiento de las imágenes estuvimos haciendo varias pruebas. Lo complejo en este caso es obtener al final esto, porque las tomas que nosotros hacemos de la pupila son muy centradas. Por eso es que tenemos un espacio especial para tomarlas, porque es muy difícil. Entonces necesitamos que la pupila no esté muy iluminada, y si no tenemos iluminación, por obvias razones, no tenemos una imagen. Entonces por eso ocupamos parte del infrarrojo. Entonces en este caso, al hacer las pruebas, lo que nosotros hacemos principalmente en el threshold, lo que hacemos es eliminar todo lo que existe detrás para tener este espacio de la pupila. Entonces este espacio, al tener el umbralizado ya, con todo este proceso que también se probó con otros acomodos, nos generó un resultado favorable. Y después del threshold, pues vimos que es necesario aplicar en este caso la cerradura de operación morfológica, para que al final hagamos un Kenny y entonces tengamos este espacio que nosotros es lo que nos interesa, el área de la pupila. Entonces a eso ya le aplicamos el ajuste de la elipse, en este caso porque pues la pupila no es circular como tal, aunque lo pareciera, y pues finalmente ya nos entrega el área pupilar, pero sí, por eso es que este umbralizado se utiliza en este caso, con lo demás que probamos.
Gracias.
No, gracias.
Any other question?
Bueno, como respondiste en español, pues te voy a preguntar en español también, ¿no? Todo este preprocesado que realizaste para los videos, veo que es pues una metodología, ¿no? Una forma de hacerlo, pero ¿has aplicado, por ejemplo, herramientas de inteligencia artificial para, por ejemplo, seguimiento de puntos y poder lograr el mismo objetivo? ¿O no lo consideraste? Porque hay herramientas que, por ejemplo, permiten definir a un video diferentes puntos de interés a poder traquear. Y veo que en tus objetivos que pusiste para trabajo futuro, pues es la extracción de ciertas características a partir de los videos, ¿no? Y siento yo que mediante ese acercamiento de puntos de interés podría servir. Entonces no sé si está considerado o lo descartaste, y si sí, ¿por qué?
En los puntos de interés, cuando mencionas, ¿te refieres a qué? ¿A segmentar un espacio para obtener la pupila? ¿O al punto de interés como tal, el área de la pupila?
A delimitar el rango de la pupila mediante diferentes puntos de interés.
Ajá, bueno, es que depende, porque en este caso hay investigaciones que ya han trabajado, donde es nada más el pupil tracker, que es el pupil tracking, que es el seguimiento de la pupila como tal.
Okay.
Pero nosotros aquí lo que estamos haciendo no es hacer un seguimiento, una detección de la pupila, sino nosotros lo que estamos trabajando es exclusivamente, y las tomas se ven en las imágenes, es exclusivamente con la pupila. Entonces, al tener este acercamiento, pues ya nosotros no tenemos que delimitar como tal, porque el riguroso, los rigurosos delimitaciones existen ya en el protocolo. Entonces, ¿qué es lo que pasa? Que nosotros no dejamos que parpadee el sujeto, o se le pide que evite parpadear, porque el parpadeo contamina esta imagen. Por eso es que tenemos el frame selection. Entonces, cuando nosotros eliminamos estos parpadeos, o en este caso cuando las mujeres se maquillan y usan mucho rímel, también eso nos provoca ruido cuando hacemos la segmentación. Entonces, el tracking como tal pues ya no es muy necesario, y eso elimina el que tengamos un proceso exhaustivo para los datos que estamos teniendo, cuando pues ya desde el protocolo que nosotros tenemos para las grabaciones pues trabajamos con las imágenes de la mejor medida.
Okay. Perfecto, gracias por la respuesta.
No,
y
gracias.
Felicidades por el trabajo.
Gracias.
Okay, thank you, Juan Carlos. And on behalf of the organizers, I have your diploma for your presentation. Thank you. And we are going to pass to the next speaker. Okay. The next talk is presented by Petra Wiederhold. The title of the presentation is on the minimal perimeter polygon for digital objects in the triangular tiling. So, are you ready? Okay. So.
Thank you very much. Thank you very much. Good morning. My talk is a little bit theoretical about a geometrical object. This is the minimal perimeter polygon. So this is the plan of my talk. I will say some words very briefly why we are interested in the triangular tiling, or triangular tiles, or triangular pixels. Then what is the minimal perimeter polygon, only named MPP? Why it is interesting or useful? Then we will come to the problem, well, how to determine this polygon. And our contribution is a new MPP algorithm, and we only need a boundary tracing algorithm. We will see an example as some conclusion. So, in the same way as we are it is very usual, very common that pixels we imagine like squares. So they are identified with the tiles of the square plane tiling. Obviously, we also could think to use the triangular tiling or the hexagonal tiling, and this is nothing new. This has been done for many years. So where the pixel, for example, are identified with equilateral triangles. So we can consider a digital object as a set of tiles, also called complex by many authors. then in the same way we are doing in the common square tiling, where we introduce certain adjacencies to receive connectivity for digital pictures. It is obviously very known. The 4 neighborhood creates the 4 neighborhood graph, or the 8 neighborhood creates another adjacency. In the same way we can say here, so 2 pixels we are considered as neighbors when they share a common side or a common edge of this tiling. So we have the edge adjacency, which creates connectivity in this type of digital plane. So here we are. Digital object then is will be considered as an edge adjacency connected complex. Complex is simply a finite set of tiles. Okay. So such pixels, or in general, using the triangular tiling as a model for digital 2D images, has been done for many years, starting with these classic work by Deutsch about thinning algorithms, where the focus is on topology preservation. But you see that are also some modern works in this regards. Then another topic is, for example, the minimum perimeter polygon we will talk about. This has been done many years ago in the 70s, very general for polygonal tilings, not necessarily square, nor triangle, nor hexagons, much more general. There is an author, Benedict Nagy, who has worked during the last 20 days many things contributing to digital geometry using triangular pixels. For example, to create digital distances, to study shorted path, combinatorics, to approximate a Euclidean disk. He started to develop mathematical morphology for images of triangle pixels and many other things. And there is also a work by a group of Indian colleagues who impose a triangular tiling on an image of square pixels. It is quite interesting to model certain images by collections of triangles which are not necessarily pixels. Okay, so the minimal perimeter polygon, or MPP, very originally has been developed and defined the first time in 1972 by these colleagues, Glansky, Chassin, Hansen, where they prove only for rectangular tilings that the MPP exists is unique for so-called regular complexes. This has been adopted by several authors, of course, to the common square tiling, and this is mentioned. Then the MPP is recommended as a model for curves or for objects in these very known textbooks whose latest editions are quite modern. The same authors partly some years later extended this theory to polygonal tilings, very general, which of course includes the case of triangular tilings, where again the existence and uniqueness of the MPP was proved for so-called normal complexes, which are a little bit more general than regular ones. So here is situated our work, regular complexes in the triangular tiling. Well, what are regular complexes, which will be the model for our digital object? Well, these are finite sets of triangular tiles, like here, edge adjacency connected, we have already fixed as a condition, and regular complexes only have no or end tiles. That means there is no tile as here, for example, which would have exactly one neighbor in the object. This is not allowed. And also, the union of the tiles belonging to an object has no hole. That's all. The very formal definition you can read in the paper. That is, I'm simplifying some things here. So, what is the MPP? First, it is a polygon, of course, yes. So, it is a special polygon which does not leave the union of the tiles belonging to an object. And only it is a condition that the polygon, please note that I'm not considering the curve as a polygon, as some authors. The polygon is the curve and all what is inside, okay? So it, but the other condition is that this polygon has to touch all the tiles which belong to the object. Obviously, these three polygons satisfies these two conditions, but we also want that the polygon has minimal perimeter among all polygons which could achieve this. So we can think here we could do a little bit better. For example, like this. These are also polygons which satisfies this condition, but they have a smaller perimeter than the previous ones. And we could do a little more better, like this, for example. And these are the polygons with minimal perimeter. These are the MPPs. We can see, for example, for this very little complex, the MPP is something very small. It is degenerated to one single point. What about this crazy object here, which is very thin? Well, here you have the MPP. The MPP can be a polygon which is not necessarily simple. It is weakly simple. Its frontier, which is drawn blue here, can touch itself, can come back on itself, but never will transversally cross itself. Okay, so why the MPP is important or interesting for image analysis? First, it is of course a compact representation for digital objects, which faithfully describes convexity and concavity properties. This has been studied many years ago for polygonal tilings, and it has been much studied in the last years, of course, for square tiles. Another interesting property is this one. The length of the MPP frontier is a multi-grid convergent estimator of the perimeter of certain sets in the Euclidean plane. What means that if you digitize these sets under increasing digitization resolution, the estimation will become better and better, and finally theoretical will converge to the true perimeter of the Euclidean figure. By the way, this has been proved formally only for square pixels. So, how to determine the MPP? Of course, it would be sufficient to determine the ordered sequence of vertices. So, of course, we have some algorithms, the classic ones of the 70s for rectangular tilings, its adaptation to the square tiling, which is reported in modern textbooks, and for polygonal tilings. Very general, very nice. They are very great papers, many pages. Unfortunately, they are all erroneous. All these algorithms are not correct. They have serious strategy errors, and there are also theoretical errors. And a very recently accepted paper shows evidence correct these errors and develops a new MPP algorithm for regular complexes in rectangular tilings, saving all correct ideas from here. To mention only, there is also related work from other areas. The MPP is also known for polygons in the Euclidean plane, where it coincides with a relative convex hull, also called geodesic convex hull. This is known for simple polygons or weakly simple polygons, where the MPP is the polygon with minimal perimeter, which includes the red polygon, but are included or constrained by the other, and here we can see this. But this for Euclidean plane, and techniques to determine this MPP come from computational geometry. They are very complicated algorithms, and they use decompositions, mainly triangulations of polygons, and are quite difficult to implement. So for this present work, we decided to contribute with a new MPP algorithm which adapts the strategies of the other one recently accepted but made for rectangular tilings, and we adopt it to triangular tilings. It is important here that we need as input data a so-called canonical boundary path, though we also need a boundary tracing algorithm, but this is something very simple. Okay? Then the MPP algorithm is based on iterative restriction of cones of visibility through forthcoming boundary tiles. It is quite easy to understand and to implement. For the conference paper of this conference, we restricted our attention to complexes with simple boundaries, which is something little special, and the correctness proof only was outlined, but now we are 2 months later, so I can say we have completed the correctness proof for regular complexes, and the algorithm works perfectly in general case. So let's see very briefly a part of an example. Here we have a regular complex, and it is very easy to determine the boundary path which is here indicated by the arrows. And as next step, it can be proved easily that this point, which is a corner of the leftmost triangle in the top row, always is an MPP vertex. So we can start with this one, and then which is the game? We will observe, due to the order in this boundary path, we will observe these edges from one tile to the next one. For example, from here to here, this is the edge, and we will see always left endpoint, right endpoint of this edge. And these actually, when one of these endpoints still coincides with this point, we will ignore them. So this is the first edge from this tile to this tile, where the two endpoints are distinct from this one. Okay? So here we start. These 2 points open a new cone of visibility through forthcoming tiles. Right corner, left corner are determined by these points, which is the next edge is this one. So right point, left point, what will happen? The left point restricts the cone of visibility. Yes, it constrains it more, and we follow these steps. So the next one restricts this point. This left endpoint restricts the cone so much that it becomes a ray, is degenerated. And what happens and this point is outside the cone to the left, and the algorithm will ignore it. Okay, in the next step, it happens something funny, because now the 2 endpoints of the next edge lie outside the cone to the right. This indicates to the algorithm that it detected an essential boundary movement to the right, and this makes find a next MPP vertex, which is this blue one. So we have find this. And now the game starts again. A new cone is opened by right point, left point. In the next edge, it is restricted by this left point. Sorry. And in the next, it is restricted again to array. The cone became array. Interestingly, this is ignored because this one confirms the cone. It's on the cone. The next one also. Outside to the right, no problem, because this one confirms the cone. Then we have distinct situation. Now the right point confirms the cone, so it is now the last point which determines the right cone border. These two in the next steps are ignored. In the next, the left point confirms the cone. That's why now this is the last point which determined the left corner border. So in the next steps are two which are ignored because this did not move. It's the same point as before. Now the right confirms the cone, but now comes some interesting. In the next step, which are the endpoints really? We have here a right endpoint, left endpoint, but seeing from this point, this is wrong, obviously. These are in the wrong direction. So the algorithms detects a movement to the left, and we have found a new MPP vertex. And it can be easily seen that the algorithm is able to find correctly the remaining points of the MPP. So to conclude, we have to say that first, to use the canonical boundary path as input is essential for the algorithm. For other boundary paths, it's not correct. Obviously, this boundary tracing is very similar to known boundary tracing for 4 contours of square pixels, for example, has linear time complexity in terms of the number of boundary tiles. It is not necessary to see all the complex in general. But the linear time complexity for the MPP algorithm is not guaranteed. There are worst cases where the complexity could be near quadratic. And future work, therefore, includes to explore and to adapt techniques from computational geometry, which in general are very complicated, but perhaps adapted to this special situation could be easier. And there are chances there to find an algorithm of linear complexity. Thank you very much.
Thank you, Petra, for your talk. Now it's time for question. Is there any question?
Hi. How much is this related with the finding the skeleton of a figure?
The skeleton is already something very thin, okay? So, of course, you could perhaps apply the MPP, but it will be also very thin. So it is not obvious at the moment if the MPP would be for such thin objects. I think that it's not the same that the skeleton. They will not coincide. But it is an interesting question to see in the future which relation could be or which properties could be shared by both objects. Thank you.
Any other question?
Just curiosity. The main example is in dimension 2. Is it possible to extend this method for higher dimensions?
Sure, but it's nothing obvious how by the moment. For example, I commented that the MPP frontier length is a multi-grid convergent estimator for curve length. And it has been proved also that in 3D, there is an equivalent concept of MPP, and the MPP area will be a multi-grid convergent estimator for surface area. This has been proved theoretically, but to my knowledge, at the moment, there is no algorithm, not yet, to determine the MPP of a 3D object. It is not the minimal area polygon, which is known. The MPP in this context, we have to be very careful, is the relative convex hull or the geodesic convex hull. It's slightly different in 3D. In 2D, we cannot see this difference, but in 3D, they are different.
Well, thank you.
Okay, thank you very much. We don't have more time, so on behalf of the organizers, I have a certificate for you, and we are going to pass the next presentation. Thank you. Okay, the next talk is presented by Jose Silvan Cárdenas, and the title of the presentation is 3 books representing building geometries extracted from point clouds.
Thank you very much. Good morning, everyone. And I'm going to present work done jointly with my graduate student Josafat Guerrero and Jose Manuel Madrigal, who is co-work at Centro Geo. And it's entitled 3 Box Representing Building Geometries Extracted from Point Clouds. Okay. Let me check if this works well. Okay. Pointer. So what are the dense point clouds? Dense point clouds are just XYZ coordinates in 3D, 3D points that are generated today in one of 2 ways, usually using a laser scanner, for instance. And we also have the UAV photogrammetry, coupled with some powerful algorithms from computer vision, which can generate things like this. This is actually a point cloud. You can see like a picture, but if you do a zoom in, you can see the individual points that they are colored from the photographs. So these point clouds are very useful because you already have the 3D structure of the objects that you map through to this method, but they are useless for handling like building information, for example, that are required in some systems. Like this is an example of a building model that can be used in some systems where you have some properties attached to all those elements of the building. So how to go from here to here is an open problem, and there are some proposals in the literature, but we are not dealing with the algorithm to transform this point cloud into a building model, but rather to how to represent this in the computer. As otherwise stated, what is the best data structure that allows us to implement such an operation? So the question is not very easy, has not a very easy answer, and there are some already proposed models like the standard CTGML, which allows to represent not only buildings but also trees and bridges and other infrastructure elements. And it also supports level of detail, which I'm going to talk about in the next slide. But this standard requires that you express the geometry of the object explicitly. So what this standard does is that allows you to describe the geometry explicitly. So in this paper, we are not competing with CTGMLs. Rather, we are trying to provide an intermediate layer between the building or the object representation in the point cloud and then the geometry. So there is an intermediate layer that allows you to go to the geometry with not much effort. And today, most of these methods to transform point clouds to the geometry are mainly shaped by the user perspective. So where are you going to use those data sets will determine the algorithm. So there are some BIMs, building information modeling management systems, the computer-aided design systems, the GIS systems, or geographic information systems. And depending on which of those systems and what applications are you dealing with is the form of the algorithm you will have at the end. And so what we are proposing in this study is that we need to use the producer perspective to take a look at what is the producer need in order to provide a better representation of the data. So the user perspective is manual editing, and there are also procedural language which can semi-automatically generate these building models. But here we are also interested in fully automatic generation, which is not yet resolved. In the CTGML standard, there are 5 levels of details called lot 0 through lot 4. In the lot 0, you only have the footprint of the buildings. It's a polygon, basically a 2D polygon, where you can attach some attributes to those polygons. There's also lot 1, which is a block model, where the height of the building is also represented geometrically. And in lot 2, you already have some details on the roofs. In lot 3, you have some architectural details of the exterior, and in lot 4, you also have details of the interior. In this presentation, we are, or our proposal only supports these 3 levels, lot 2 and all other, lot 0 and 1. And the method is, or at least the proposal is very straightforward. You start with a dense point cloud. You can either generate some key points manually through manual selection or automatic selection. This part is not still working, but this one is already implemented. I'm going to show some example of that. And then those key points allows to build some, to represent some buildings, and which can also be further edited through this block. And then at this point, you don't have the explicit geometry. And then through build surf, you generate the geometry, and then you can do what you usually do in systems handling this type of data. So the contribution is mainly on how these building primitives are represented, basically. So building primitives are composed of 3 parts, basically: floor, walls, roofs, and each of them has have their attributes which define their geometry. And in the paper, there is a full list of these attributes and with descriptions and also equations. And the idea is that this part composes a building part or a building primitive, and building complexes or buildings are aggregated of those parts. And there is also the problem of how to relate those parts, which is not addressed in this work. Okay, go back. The idea is to represent the geometry implicitly is through transformed rings. Basically, you have a set of rings that are related through some transformations, linear transformations, and the minimal parameters that are needed to go from one base to another level is just some shift parameters, what we call shift parameters or relative shift parameters, alphas, gammas, and beta. And so all those parameters are plugged into a geometric transformation, which allows you to generate all the rings of the buildings. And in that way, you don't have to express all the full geometry, but only those shift parameters together with other more global parameters like size and orientations. And for example, we generated a library of different type of roofs expressing the shift parameters like this. For instance, 50, 50, 0 means that the alphas are 50, the beta are 50, and the gamma are 0. So there is no displacement or shift in the C direction. You end up with a flat roof. In the 50 and 50, you can think that the displacement of this side of the ring to the middle and this side of the ring to the middle in both directions. And so you end up with the ring collapsing to a point, basically. And the rings that are transformed retain the same number of vertices. So in that way, the triangulation of the surface is straightforward. So you can use this way of representing the rings, basically with these shift parameters, and with the advantage that you don't have to express the shape of the floor plan or the footprint of the building. So you can have a square or rectangular footprint, round or elliptical, or even polygonal, which is limited to star-shaped polygons. Star-shaped polygons means that there is a point in the polygon that can see all the points inside the polygon. And there's a problem here for our previous presenter, how to decompose the general polygon into star-shaped polygons or even convex polygons. That is something that has not been solved, to my knowledge. And so one of the things that we wanted to do is to test this representation of buildings, see if we can generate those without explicitly saying the geometry of each of those units. So here's an example. We generated a procedural macro language to procedural generation in which you manipulate a given unit. For example, we start with this rectangular unit here. Of course, I'm showing here the geometry, but in the computer there is no geometry. There is just a bunch of parameters, the shifts and the sizes and rotation, etc. And so we operate on those parameters only. Say, for example, copy first, resize 0.5 along Y, move right of first, align from first. So basically, this is generating this number 2 polygon out of the 1, and then copy last, move back. Also copy this one and move it back. That is the third, and so forth. So executing all this instruction will generate all these elements, and so that you can build something like this in an easy form. And I am skipping a lot of things that are in the paper, but here this part I didn't include it in the paper because it spent a lot of space. But basically, this is only the description of the transformation and the illustrations, how the transforms that were defined perform, like move, align, and mirror, are some basic operations that act on the 2D and the 2 dimension on the floor plane. And here's a point cloud of the INEGI complex in Aguascalientes, which was generated with a few hundreds of photographs, aerial photographs taken through a UAV, unmanned aerial vehicle. And then using these macro languages, we were able to build this part. So what we did was first generate manually one of these blocks, and then through just transforming those parameters for that block, we were able to generate this complex, and then express the geometry through the build surf function. This is another example of Centro Geo complex in Mexico, and I'm going to skip. This is the Church of Tepepan, and I'm providing here a URL where you can see the point cloud interactively and put the mesh, also the object, and compare with the point cloud. So these are how it works so far, and our aim is that we can generate later this fully automatically. Right now it's only semi-automatic. This is the UPN in the Universidad Pedagógica Nacional in Mexico. And of course there are some complex buildings that cannot be represented with this data model. Some of them are listed here, like this complex curved buildings, or this bochka type, or this round with holes, this rhombic. These are not representative. You can prove this because you cannot generate rings that are isomorphic with some transformations and for this kind of structures. Well, just in conclusion, tree box is a geometry-free representation of buildings, so there's no geometry explicitly, it's implicit, and supports the LOD2 of CTGML with high flexibility. As you can tell, you can, through the parameters, generate different type of building roofs. Support manual and procedural generation of building primitives. The macro language exploits the spatial relationship of building primitives. This is important because it keeps tracks of these relationships, which can be later on used for the semantic relationship of the building. Easy generation of repetitive building complexes. Point clouds use it to key point selection and post-production adjustment. I didn't mention a lot of these post-adjustments because we are still working on that. We have done some progress on that. And the question still remains that can this data model facilitate the automatic generation of buildings? We still are working on that. So I appreciate your time. Thank you very much.
Thank you, Jose, for your presentation. Now it's time for questions. No questions? Okay.
Thank you. How do you quantify the quality of or the detail of your point cloud?
The point cloud has several steps of productions, and there are some metrics like the point density, for example, but there is no warranty of quality. What I mentioned in the paper is that we use GPS to measure some control points across the Centro Geo building, and measure the errors of the point cloud, the root mean square error for those points that were measured with a high precision GPS. And we found that it was 1.5 centimeters when we used the ground control points. And when we didn't use those ground control points, it was around 15 centimeters. So because the INEGI norm that says that with 20 centimeters you are okay in cadastral application, then we say we don't need ground control points, because ground control points are very hard to collect. It takes a lot of time. So we didn't took any more control points for the other data sets. Yeah.
Any other question?
Thank you for the presentation. My question is how can you generate the surface based on these coordinates on X, Y, Z?
Okay. The main idea is to have the footprint. I mean, the polygon, the base polygon, is the first geometry you need to generate. So if the user specify a square footprint, then you only need the length and the width. Also, of course, the position of the building, the center, and its orientation. So those are parameters that are listed in the paper. And with all those parameters, you can generate the footprint, the polygon of the. And then with the shift parameters, you can generate the upper rings by just stretching the rings, the original ring, and shifting up. And in that way, you build the surface. I'm not sure I was clear.
I mean, I'm thinking about maybe marching cubes algorithm, something like that, to construct the surface. But thank you.
There is no fitting here, but only some key points from the point clouds that were selected to generate to generate some parameters for some of the units, and some other units or primitives were generated automatically. So there is an adjustment, a further adjustment to basically apply again the point cloud, the full point cloud to the surface to adjust the parameters, but that part is not included in here.
Thank you.
Yeah.
Well, thank you for your talk, Jose. And this is the certificate for your presentation. And we're going to pass the last talk of this session. And this is presented by Daniel, is right? Okay. Daniel Martinez Barba. And the title of this presentation is From Front to Bird's Eye View, Transformation for Autonomous Vehicles, a class imbalance-based approach. Okay, go ahead.
Thank you. Hello and good day, everyone. My name is Daniel Martinez. I am representing the Intelligent and Autonomous Systems Lab from Centro de Investigaciones en Óptica in Aguascalientes. Today, I am very excited to share with you our work titled Front to Bird's Eye View, Transformation for Autonomous Vehicles, a class imbalance-based approach. And yeah, let's start. This is the outline that we will review on this presentation. And I want to talk with you about the last decades, where we have seen an increasing growth on the cities due to the advancements on technology and industry. We've seen how the internet evolves, how powerful computers, virtual and augmented reality, and of course, artificial intelligence. However, as the cities keep growing and the population increases and the number of vehicles as well, other type of problems have arisen. For instance, environmental and road safety concerns, which are caused by inefficient transportation media and also reckless driving, respectively. Electric and autonomous vehicles have been proposed as a solution to improve both environmental and road safety concerns. But these are all old news, right? We already know that even though these systems are far from perfect, they are already operating at China, some countries in Europe, the United States, etc. But how do they work? We could summarize the pipeline of an autonomous navigation system with this process. I want especially to focus on the environmental perception model, which is the one that handles the acquisition of sensor data and transform it into a scene representation. This scene representation of the urban scenes is crucial to the correct operation of an autonomous system, because other subsequent modules of decision making, such as local road planning or localization, etc., depend upon a good representation of the scene. Most commonly used on robotics or on autonomous vehicles, we use occupancy grid maps to represent the environments which are captured or acquired by sensors like cameras, LIDAR, radar, etc. For this work, we are particularly interested on creating these scene representations from monocular front perspective images, and build this type of top occupancy grid maps, also called bird eye views. But these occupancy grid maps are not a new concept, so why would we still use them for these applications? So the bird eye view maps are a very intuitive way to represent the urban environments. It is very easy to integrate different type of sensor data into this type of representations. And also, as seen in figure 7, we can also add semantic information, all object detection and lane detection, etc. As seen in the figure, for example, we can represent the different semantic classes on this bird eye view. And yeah, also, and most importantly, this type of bird eye views have shown interesting results on the autonomous navigation road planning using deep learning. So regarding the perspective transformation from monocular front perspective images into bird eye view images, in the literature we've seen that researchers have developed algorithms to transform these images using deep learning algorithms that include models like inverse perspective transformations, generative adversarial networks, variational autoencoders, and of course, vision transformers-based architectures. So even though each iteration or each model keeps improving the performance of this perspective transformation task, this is still not a solved task. We've identified a couple of challenges. For instance, how to acquire bird eye view ground truth to train our neural networks, and also how to improve the semantic segmentation of these bird eye views, especially for the minority classes at the pixel level, because this the representation of these urban scenes is a highly imbalanced class at the pixel level. For instance, there are a lot more pixels from, let's say, the drivable area or non-drivable area than for classes like vehicles or pedestrians. So this imbalance causes a bias on the models. So there's still a lot to do about these imbalanced data sets. So we pondered about these challenges, and what we proposed in this work is an exploration of the intricacies of the task of transforming a monocular front perspective view into a a bird's eye view map, a semantically segmented bird's eye view map, as we see, for example, in these images. In this work, we implemented, trained, evaluated, and compared a couple of models of the state of the art for perspective transformation. We explore how to balance or how to improve the performance of semantic segmentation using different loss functions. And we also, to overcome the data limitation, we proposed a data augmentation technique for autonomous vehicles. So yeah, in this work, we try to explore all the interactions between the models, the loss functions, and the data augmentation to investigate how to improve the performance of semantic segmentation for this task of transforming a front view into a bird's eye view map. Let's review the methodology. First, we proposed to acquire a synthetic dataset. We used the Carla simulator, which is an open source research simulator for autonomous vehicles. It's a very convenient tool because it provides a powerful and useful API that allows to control every element of the simulation. Based on this API, we built our own wrapper tool or our own framework to easily design and execute autonomous vehicles experiments. As for now, the main feature of our framework is a scene generation, an automated scene generation tool, which allows us to automatically generate data sets for autonomous vehicles experiments. How does this work? Well, this uses a scene configuration file where the user defines a couple of points, initial and final waypoints, to create a route. Then the ego or hero vehicle is spawned at the initial waypoint. The algorithm then detects which roads pass through this route, and a defined number of vehicles and pedestrians are spawned at the route. So we can create a vividly traffic scene on this between these 2 points. So then the traffic scene starts, and the ego vehicle starts acquiring sensor data to create our dataset. This is a sample of our dataset. It consists or is integrated by 2 images. On the left, we have the monocular front image, which is an RGB image, and on the left we have a top semantic view or a bird's eye view with the cityscapes palette. The cityscapes is a dataset used for autonomous vehicles, and this is an image that contains semantic masks for different classes. Here we are only interested in 5 classes, which are non-drivable, drivable, the walkways, vehicles, and pedestrians. Also, we proposed a data augmentation technique, which we call layer-based data augmentation. This is based on one of the features of the Carla simulator, which allows us to render different object layers in the map. For instance, we can choose to render or not layers as the buildings, the trees, the road lines, the fences, etc. We have control over every layer. So we developed this, or we proposed this technique as we hypothesized that the deep learning models could learn different representations of these perspective transformations using different levels of information. So for this augmentation, we're using three samples, or the augmentation has 3 images. This is the original image called traffic. This is just the normal traffic that contains all the information. Then we have the layer sol, which has every object in the map except the dynamic classes, which are the pedestrians or the other vehicles. And then we have an augmented sample called layers none, which only contains the roads. After acquiring the dataset, we have a small post-processing pipeline to generate our ground truth generation, of course, to train our deep learning models. So here we have the raw input image, which is then resized into a lower resolution image, and also the colors are remapped into our 5-class palette. This resizing, of course, generates noise, which is cleaned by an erosion morphological operation. Then at the end, we use a dilation operation, but only on the dynamic classes, which are the vehicles and the pedestrians. This allows us to represent these objects bigger than they are in these bird's eye view maps. So after generating ground truth, we have the dataset, which we acquired with our scene generation tool. It contains 13 scenes on 3 of the maps of the Carla simulator. These maps have different architectural styles and lighting and environmental conditions. So the training set, let's say this is not the non-augmented dataset, so it will only contain the traffic images. And the training set will contain the scenes from the map 1. It is validated with an on-scene scene from also map 1. And then for the generalization test, we are using scenes from the never seen maps. Yeah, so these are the models that we implemented for our experiments. We have the variational encoder decoder and also a pyramid occupancy network. We chose these models from the perspective transformation literature because we wanted to contrast different architecture paradigms. On the one hand, we have a classical variational autoencoder, which only uses convolutional layers. And on the other hand, we have a novel architecture that that transforms these monocular front images to the bird's eye view maps using a transformation that includes the focal length of the camera. So these camera parameters are used inside the network to provide a better perspective transformation from the front domain into the bird's eye view map. So the experiments, first we wanted to explore how to balance the semantic classes using different loss functions. The way it's done is, the way we executed this experiment, we have the cross entropy loss function because we are using a semantic segmentation task. Here we have defined the cross entropy loss function. This doesn't have any weights. Then we have 2 functions which weights of the semantic classes are defined by their inverse frequency appearance, or no, yeah, by their inverse frequency on the dataset. So the lower the appearance of these classes, the higher the weight it is for the loss on the optimization process. And finally, we have the recall cross entropy, which is a function that updates its weights based on a class-wise false negative rate. These are the results for this experiment. First, we can observe from this table that the variational encoder decoder is much more sensitive to the changes of the loss functions than the pyramid occupancy network that has a more uniform behavior. But most importantly, we can see that the best performant loss function is the squared root inverse frequency cross entropy function for both models. not only in the mean intersection over union metric, but also on the dynamic classes, which are the minority classes, which are vehicle and pedestrian. So as we obtained that this was the best loss function for this problem, we kept using this function for the following two experiments. This is the data augmentation experiment where we compared a non-augmented dataset with a classic data augmentation and also our layer-based data augmentation. As we said before, the non-augmented dataset contains only the images of the scenes with the traffic samples. Then the classic data augmentation has the training set has 3 times the size of the non-augmented set, but it's augmented. The traffic images are augmented with classical operations like the Gaussian blur or vertical flip. And the proposed training set, which uses our method, the layer-based data augmentation, has also 3 times the size of the training set, but we use the augmented samples that we talked in the other slide. So these are the results for this experiment, and from here we can see that unsurprisingly the augmented training sets yielded a better performance on the semantic segmentation for both models. But we can also see a slight improvement with our method, the layer-based data augmentation, in both models. It is just a slight improvement, but not only in the mean intersection over union, but also on 3 or more of the individual intersection over union metrics for the individual classes. Finally, the last experiment was the generalization one, which we used the same models trained on for these results, but these are evaluated against the test set or the generalization set, which contains scenes that were never scenes from maps that were never seen by the trained models. So this is supposed to be a very hard test for our models because these other maps contains different lighting settings or different architectural styles on the maps. So these are the results for this final experiment. And let me explain this figure. Here we have plotted on these bars the individual intersection over union metrics for each non-augmented and augmented models for both the variational encoder-decoder and the pyramid occupancy network. And on the blue data points, we have the mean intersection over union for each model. So first of all, we can see that the mean intersection over union metric overall decreased for all models. This is is due to the complexity of this new generalization dataset. But also, contrary to our findings on the second experiment, here the classic data augmentation has a better performance on the variational encoder-decoder model and just a slight better performance in the pyramid occupancy network. However, as for now, we are trying to create different subsets or combinations of both classic and our layer-based data augmentation to investigate how to keep improving the performance on the dynamic classes, which are the minority or the imbalanced classes on the segmentation problem here. Okay. Yeah, this is just the conclusion. I had a demonstration video, which is the inference. But as the conclusion, we have designed and acquired a synthetic dataset for front to bird's eye view perspective transformation using our scene generation tool. We also implemented, trained, and tested these deep learning models to transform monocular front perspective images into bird's eye view maps. We explored the effects of loss functions to address the class imbalance for semantic segmentation. And we proposed and evaluated a data augmentation approach using the Carla simulators features. And yeah, these are the references used for this presentation. And that's all. Thank you.
Thank you, Daniel, for your presentation. Now is time for questions. Okay, we have time for one question.
Hi. How many layers does the autoencoder or the has?
Well, the variational autoencoder first uses a BGG16 backbone, and then here we have a BG16 backbone which has 16 layers, and then the encoder has another block of maybe like 10 layers of these convolutional layers to encode the information into this latent space. Then, as we know, this pattern is repeated. It's repeated inversely to create the representation.
Okay, thank you. And the time is over, so thank you to Daniel for the presentation. And this is the certificate for you. And thank you to all of you for being here in this first session. Now we have the coffee break, so please take maybe a couple of minutes or 3 for some coffee, but we have to start immediately the second session. Thank you.